Welcome to this coding walkthrough for LeetCode problem number 980, Unique Paths 3. In this session, we'll tackle an intriguing problem that involves finding unique paths on a grid while following specific constraints. By the end, you'll have a solid understanding of the problem and the strategies to solve it. Let's dive in. In this problem, we are working with a grid represented as a 2D array of integers. Each cell in this grid can have one of four values: 0, which indicates a traversable empty square, 1, which marks the starting square where our path must begin, 2, which represents the ending square where our path must terminate, and -1, which indicates an obstacle square that cannot be traversed. The goal is to find the number of unique paths that start at the square marked with a 1 and end at the square marked with a 2, under two key conditions. First, every non-obstacle square must be visited exactly once during the path. Second, the movement is restricted to the four cardinal directions: up, down, left, and right. The input to the problem is the grid itself, which has dimensions m by n, where both m and n range from 1 to 20. The output is an integer representing the total number of such unique paths that satisfy the given conditions. To better understand the problem, let's look at an example. Suppose the input grid is a 3x4 grid, where the starting square is located at the top left corner, marked with a 1, and the ending square is near the bottom right corner, marked with a 2. The grid also contains an obstacle square, represented by -1, located in the bottom right corner. In this setup, there are exactly two unique paths that meet the problem's conditions. These paths start at the square marked 1, traverse every non-obstacle square exactly once, and terminate at the square marked 2. Let's explore what these paths look like to see how the conditions are satisfied. The first valid path starts at the top left corner, moves to the right through all the squares in the top row, then continues downward along the rightmost column, and finally zigzags through the middle row until it reaches the ending square. The second valid path also begins at the top left corner, but this time it moves downward first, then traverses the middle row entirely, moves upward along the rightmost column, and finally zigzags through the top row to reach the ending square. Both of these paths visit every non-obstacle square exactly once and conclude at the square marked 2, fulfilling the requirements of the problem. This example demonstrates how different traversal orders can still satisfy the same constraints. Now consider another example where the grid is still a 3x4 matrix, but this time there are no obstacles. The starting square is at the top left corner, and the ending square is at the bottom right corner. In this scenario, there are four unique paths that satisfy the conditions. Each of these paths visits every non-obstacle square exactly once, but they follow different traversal orders to reach the ending square. On the other hand, in a smaller grid, such as a 2x2 matrix where the starting square and ending square are positioned diagonally, it may be impossible to find a valid path. For instance, if the grid is arranged in such a way that every non-obstacle square cannot be visited exactly once while moving from the start to the end, the output will be 0, indicating no valid paths exist. Finally, let's consider the constraints and edge cases that might arise in this problem. The grid size is limited to dimensions ranging from 1x1 to 20x20, and each cell in the grid can only contain one of four possible values: -1, 0, 1, or 2. Importantly, there will always be exactly one starting square and one ending square in the grid. Some edge cases to keep in mind include grids where obstacles block all possible paths, making it impossible to find a solution, or grids with only one valid path due to limited movement options. Additionally, the problem complexity can increase significantly when the grid is large and contains many empty squares, as this leads to a greater number of potential paths. By carefully considering these constraints and edge cases, you can better design an efficient solution to this problem. To solve the Unique Paths 3 problem, we considered several approaches. The first, a brute force method, is the most straightforward. The intuition here is to try all possible paths from the starting square, labeled as 1, to the ending square, labeled as 2, ensuring that every traversable square, or 0, is visited exactly once. We would implement this using backtracking, where we explore all possible paths recursively. At each step, we move to a valid neighboring cell, mark it as visited, and continue until all empty cells are covered and we reach the destination. However, this approach has significant drawbacks. Its time complexity is exponential in the number of empty cells, as it explores all permutations of paths, and its space complexity is proportional to the grid size due to the recursion stack. As a result, this method is inefficient for larger grids. Instead, we chose an optimized backtracking approach. The key optimization here is to track the total number of empty cells at the start and decrement a counter each time we visit one. This ensures that we only pursue valid paths that meet the problem's requirements. The implementation remains similar to brute force but with added logic to prune invalid paths early, making it a more efficient solution. The optimized backtracking approach improves on brute force in both time and space complexity. The time complexity is O(4 to the power of k), where k is the number of traversable cells, including empty cells, the start, and the end. The space complexity remains O(m*(n) for the recursion stack, where m and n are the grid dimensions. A key advantage here is that the pruning of paths which don't visit all empty cells or become invalid greatly reduces unnecessary computations, making it feasible for larger grids. Another alternative we considered is a dynamic programming-based approach. The intuition here is to track visited states for each cell while counting unique paths. This could be implemented using memoization, with the visited state represented as a bit mask. Recursively, we would compute the number of paths from the current cell to the destination, updating the bit mask as we go. However, the DP approach has significant drawbacks. Its time and space complexity scales poorly, with time complexity at O(m*(n)(2)(m*(n), and similar space requirements for memoization. The overhead of managing states in memory makes it impractical for larger grids, even though it is conceptually a valid approach. After evaluating multiple approaches, we chose the optimized backtracking strategy as our final solution. It strikes the right balance between efficiency and simplicity. First, it is computationally efficient, pruning invalid paths early and avoiding the exponential state space explosion associated with dynamic programming. Second, the implementation is straightforward and avoids the complexity of state management and bit masking, making it easier to understand and maintain. Finally, it is scalable, handling grids up to the constraints, such as 20 by 20, within reasonable time limits. While the brute force approach is conceptually simple, it becomes infeasible as the grid size grows due to its exponential complexity. On the other hand, dynamic programming introduces excessive memory and computational overhead, making it less practical despite its theoretical correctness. In summary, the optimized backtracking approach offers the best combination of feasibility, performance, and clarity, ensuring that all problem constraints are met effectively. To solve this problem, we need to find all unique paths from the starting square, labeled as 1, to the ending square, labeled as 2, while ensuring that every traversable cell, represented by 0, is visited exactly once. The grid also contains walls, represented by -1, which cannot be crossed. Importantly, the grid is structured such that there is exactly one starting square and one ending square. We break the solution into clear steps. First, we parse the input by identifying the grid dimensions, the locations of the start and end squares, and counting the total number of traversable cells, including the start and end. Then, we define a backtracking function that will handle the exploration of paths recursively. This function will take parameters like the current position, the grid state to track visited cells, and a counter for the number of squares visited so far. We also define base cases for the recursion. If the current position is out of bounds or hits a wall, the path is terminated. If the position reaches the ending square and all traversable cells have been visited, we record that path as a valid solution. If the current position reaches the ending square but not all traversable squares have been visited, the path is also terminated, as it does not satisfy the problem's constraints. The next step is the heart of the algorithm, recursive exploration. Here, we mark the current square as visited by modifying its value in the grid, for instance, changing a 0 to -1. This ensures that we don't revisit the same square in this path. Then, we explore all 4 possible directions up, down, left, and right by computing the new positions for each direction and calling the backtracking function recursively with these updated positions. After exploring all directions, we backtrack by unmarking the current square to restore its original state. This allows the square to be revisited in alternative paths, which ensures we explore every possible route. For optimization, we can prune paths early by checking if the remaining unvisited squares are fewer than the number needed to complete the traversal. Additionally, we use a counter to track the number of visited squares efficiently, avoiding redundant calculations. There are several key insights behind this algorithm. First, backtracking is the foundation of the solution, as it allows us to systematically explore every path and revert changes to the grid to enable exploration of other paths. Second, pruning is critical to reducing computational overhead. By terminating paths that are guaranteed to be invalid, we avoid unnecessary calculations. Third, mutating the grid directly to track visited squares simplifies the implementation but requires careful handling during backtracking to avoid introducing errors. The entire problem can be thought of as finding permutations of grid traversal that meet the constraints. Now, let's consider the data structures used. The grid itself, represented as a 2D list, is the primary structure for tracking the state of the problem. We also use counters, such as traversable_count for the total number of squares to be visited and visited_count for the number of squares visited in the current path. Finally, the recursive stack, which is implicitly managed by the function calls, tracks the state of each traversal step, making backtracking possible. When implementing this algorithm, it's important to account for edge cases. For small grids, such as a 1x1 or 2x2 grid, the algorithm must handle scenarios where there is only one or a very limited number of traversable squares. For grids with blocked paths, the algorithm should terminate gracefully when no valid path exists. Additionally, if the grid contains multiple isolated regions of traversable squares, the algorithm must ensure that these are not incorrectly included as part of the solution. From a complexity standpoint, the time complexity is O(4 to the power of t, where t is the number of traversable squares. This is because each square can have up to 4 possible moves. The space complexity is O(t), driven by the recursive call stack used in backtracking. Together, these insights and considerations allow us to solve the problem efficiently while adhering to the constraints. Here, we begin by defining the function uniquePaths, which takes the grid as input. The first step is to determine the dimensions of the grid, represented by rows and calls. We then initialize variables to track the start and end positions, as well as a counter, empty_cells, to record the number of traversable cells in the grid. Next, we iterate through each cell in the grid using nested loops. If we encounter A1, we record its position as the start point. Similarly, if we find A2, we record its position as the end point. For cells with a value of 0, we increment the empty_cells counter. This setup ensures we know the key points of interest and how many empty cells must be traversed for a valid path. Following this, we define the backtrack function, which is responsible for performing the depth-first search. The base case for this function checks if we've reached the end cell and confirms whether all empty cells have been visited. If both conditions are met, it returns 1 to indicate a valid path, otherwise, it returns 0. To avoid revisiting cells, we temporarily mark the current cell as visited by setting its value to -1. We also initialize a paths counter to accumulate the number of valid paths found during the exploration. Now, within the backtrack function, we explore the 4 possible directions: right, down, left, and up. For each direction, we calculate the new coordinates, NX and New York, and check if they are within the grid boundaries. Additionally, we ensure the new cell is either an empty cell, represented by 0, or the end cell, represented by 2. If these conditions are met, we recursively call backtrack on the new position, decrementing the remaining counter if the cell being visited is empty. This recursive exploration allows us to traverse all possible paths while ensuring each cell is visited only once per path. After exploring all directions, we restore the current cell's original value to allow other paths to reuse it during subsequent recursive calls. Finally, the function returns the total number of valid paths discovered from the current position. To kick off the process, we call the backtrack function with the starting position and the count of empty cells. The result of this initial call is the total number of unique paths that meet the problem's requirements, and we return this value as the output of the uniquePaths function. In this implementation, we define a public method called uniquePaths that takes a 2D grid as input. The grid represents the puzzle, where 1 is the starting point, 2 is the end point, and 0 represents empty cells we need to walk through. We start by initializing variables to store the dimensions of the grid, the coordinates of the start and end points, and a counter for the number of traversable empty cells. Next, we loop through the entire grid to identify the starting and ending positions based on the values 1 and 2, respectively. At the same time, we count the number of empty cells, which will help us ensure all required cells are visited. Finally, we call a helper method, backtrack, passing the grid, the starting coordinates, the ending coordinates, and the count of empty cells as parameters to begin the recursive exploration. The backtrack method is where we perform the recursive depth-first search to explore all possible paths. First, we check if the current cell is the endpoint and whether we've visited all required empty cells. If both conditions are met, we return 1 to indicate a valid path. Otherwise, we mark the current cell as visited by temporarily setting its value to -1. Then, we initialize a variable to track the number of valid paths and define the 4 possible movement directions: right, down, left, and up. For each direction, we calculate the new coordinates and check if the move stays within bounds and leads to either an empty cell or the endpoint. If valid, we recursively explore from the next cell, decrementing the count of remaining empty cells if the next cell is an empty one. After exploring all paths, we restore the current cell to its original value to backtrack properly. Finally, we return the total number of paths found from this recursive call. Here, we have a small grid as our first example with an input of 1002. The grid has only 1 row and 4 columns. The start position is at 0, 0, where the grid value is 1, and the end position is at 0, 3, where the grid value is 2. There are 2 traversable empty cells, represented by 0s, so empty_cells equals 2. We solve this problem using backtracking. Starting at 0, 0, we mark it as visited by setting the grid value to -1. From here, we explore the neighbors. The only valid neighbor is 0, 1, since it contains a 0. We then move to 0, 1, and continue the process with remaining now reduced to 1. At 0, 1, we again mark it as visited by setting its value to -1 and explore its neighbors. The next valid neighbor is 0, 2, which contains a 0. We move to 0, 2, with remaining now becoming 0. At 0, 2, we mark it as visited by changing its value to -1 and check its neighbors. The valid neighbor here is 0, 3, which is the end position marked as 2. We move to 0, 3, and reach our base case, where we have visited all empty cells and reached the endpoint. This constitutes one unique path, so we return 1. After this, we backtrack to restore the grid state for further exploration, resetting the cells 0, 2, 0, 1, and 0, 0 to their original values. The output for this example is 1. In our second example, the grid has an input of 1000-10200. Here, we have a 3x3 grid with the start position at 0, 0, and the end position at 2, 0. There are 5 traversable empty cells, so empty_cells equals 5. Using backtracking, we start at 0, 0, mark it as visited, and explore its neighbors. The valid neighbor is 0, 1, so we move there, reducing remaining to 4. At 0, 1, we mark it as visited and explore its neighbors. The valid neighbor is 0, 2, so we move to 0, 2, with remaining now becoming 3. At 0, 2, we mark it as visited and continue exploring. From 0, 2, the valid neighbor is 1, 2, so we move there with remaining reduced to 2. At 1, 2, we mark it as visited and explore its neighbors. The valid neighbor is 2, 2, so we move to 2, 2, with remaining now becoming 1. At 2, 2, we mark it as visited and explore further. The valid neighbor is 2, 1, so we move there with remaining reduced to 0. At 2, 1, we mark it as visited and explore its neighbors. The valid neighbor is 2, 0, which is the end position. Moving to 2, 0 brings us to the base case where all empty cells have been visited and we've reached the endpoint. This forms one unique path, so we return 1. After completing the path and returning the result, we backtrack to restore the grid state for other potential paths. However, in this example, no additional paths are possible. The final output for this grid is 1. Now let's examine a scenario where no valid path exists at all. Consider the next example where the input grid is 10-12. In this case, the grid is a 2 by 2 grid with the start position at 0, 0, and the end position at 1, 1. There is only one traversable empty cell, so empty underscore cells equals 1. Starting at 0, 0, we use backtracking with remaining equals 1. From here, we explore the neighbors. The valid neighbor is 0, 1, so we move there and mark it as visited, reducing remaining to 0. At 0, 1, we explore the neighbors again, but the only neighbor leading to the endpoint, 1, 1, is blocked by an obstacle indicated by -1. With no valid paths left, the function returns 0. The output for this grid is therefore 0, as there are no ways to traverse from the start to the end while visiting all empty cells exactly once. To analyze the time complexity of this solution, we start by considering the recursive traversal process. The algorithm explores all possible paths from the starting cell to the ending cell using backtracking. At every cell, there are at most 4 possible directions to explore: up, down, left, and right. Once a direction is chosen, the algorithm moves to the next cell and continues the search recursively. The depth of this recursion tree is determined by the number of empty cells on the grid, denoted as e plus 1 for the starting cell. Because each cell can branch into up to 4 directions, the total number of recursive calls in the worst case is proportional to 4 raised to the power of e, or 4 to the power of e. Additionally, for every recursive call, the algorithm performs checks to ensure the current position is valid, which involves constant time operations. These checks include verifying that the cell is within the grid bounds and has not already been visited. These constant time operations are repeated for each branch, but they do not affect the overall exponential complexity driven by the recursive traversal. Before diving into the recursive backtracking, the algorithm performs a preliminary step that involves traversing the entire grid once. During this traversal, it identifies the starting and ending cells and counts the total number of empty cells. This initial pass through the grid takes m*n time, where m and n represent the dimensions of the grid. However, this step is negligible compared to the exponential complexity of the backtracking process, so the overall time complexity remains 4 to the power of e. Now switching to space complexity, the primary contributor is the recursion call stack. Since the recursion depth corresponds to the number of empty cells, e plus 1 for the starting cell, the space used by the call stack is proportional to e. Additionally, the algorithm modifies the grid in place to mark cells as visited, meaning it does not require additional memory for grid storage. The grid itself, being an input, is not considered extra space. Therefore, the space complexity is dominated by the recursion stack, which is e. Another minor factor in the space complexity calculation is the use of a constant number of additional variables. These include values like the coordinates of the starting and ending cells, as well as the count of empty cells. These variables require a fixed amount of memory, which is independent of the grid size or the number of empty cells. Consequently, they do not contribute to the asymptotic space complexity, which remains e. Now considering specific cases, the best case scenario occurs when the grid is small, and the number of empty cells is minimal. Here, the time complexity is still 4 to the power of e, but the actual runtime is faster due to fewer recursive calls. On average, the algorithm explores all possible paths, resulting in the same time complexity of 4 to the power of e. The runtime, however, depends on the number of valid paths and the placement of obstacles. In the worst case, when the grid has no obstacles and is completely open, the algorithm must explore all permutations of the empty cells. This scenario maximizes the size of the recursion tree, leading to the highest runtime of 4 to the power of e. When comparing this optimized backtracking approach to a brute force method, the advantage becomes clear. A brute force method would generate all possible paths through the grid and then filter out the ones that do not meet the problem's constraints. While both approaches share the same time complexity of 4 to the power of e, the brute force method requires additional memory to store all possible paths, making it less efficient. The optimized backtracking solution, on the other hand, uses in-place grid modification to avoid this extra memory usage. It also terminates recursion early when it detects invalid paths, such as reaching the end cell with unvisited empty cells remaining. To understand the mathematical justification for the time complexity, we note that the recursion tree has a branching factor of 4, corresponding to the 4 possible directions, and a maximum depth of e+1, as the algorithm explores all empty cells. This results in a total of approximately 4 to the power of e recursive calls. Space complexity is determined by the maximum recursion depth, which is e. Both time and space complexities are thus dominated by the backtracking process, confirming the final complexities of O, 4 to the power of e, for time, and O, e, for space. When solving problems like unique paths 3, there are several common mistakes to watch out for. First, not considering all valid paths can be a major issue. Some solutions might skip exploring certain possibilities, leading to missed solutions. It's important to ensure your logic thoroughly explores every potential path from the start to the end. Another frequent pitfall is failing to account for all zero squares. In this problem, every zero square must be visited exactly once, and neglecting this requirement or implementing it incorrectly can result in invalid solutions. Infinite loops in recursion or backtracking are another challenge. Without properly defined base cases or effective tracking of visited squares, your recursion might revisit the same squares endlessly. To avoid this, ensure you mark squares as visited and carefully backtrack. Finally, edge cases like grids with no valid paths, inaccessible start or end squares, or complete blockage by obstacles are easy to overlook. It's crucial to test for these scenarios and handle them explicitly in your code. Inefficiency is another common challenge when solving problems like this. Brute force solutions that explore all possible paths without pruning invalid ones can quickly become computationally expensive, especially for larger grids. To address this, optimize your solution with techniques like memoization or by terminating early when a path becomes invalid. In interviews, clarity in your approach is essential. Clearly explain how you plan to explore paths, whether using DFS, BFS, or backtracking, and demonstrate how you validate constraints like visiting all zero squares. It's also important to discuss trade-offs. For instance, while brute force might be simple to implement, it's inefficient, and techniques like pruning or memoization can significantly improve performance. Additionally, be ready for variations of the problem. An interviewer might introduce weighted paths or ask for the shortest valid path, so practice thinking on your feet. Finally, verbalizing your thought process is key. Explain each step, including base cases, recursive calls, and backtracking, to show your understanding of the algorithm and build confidence in your solution. For additional practice, there are several related problems that can help reinforce your understanding. Unique Paths 3 itself is a great example, as it focuses on visiting all zero squares exactly once. Another is word search, where the challenge lies in grid traversal to find specific words using backtracking. Surrounded regions applies flood-fill algorithms to manipulate grids, while number of islands requires grid traversal to count connected components. Each of these problems has unique nuances that can enhance your problem-solving skills. When considering alternative approaches, brute force using DFS is a straightforward option. While simple to implement, it's inefficient for large grids because it explores all paths indiscriminately, so it's better suited for small grids or loose constraints. Backtracking with pruning is a more efficient alternative, as it eliminates invalid paths early on. However, it requires careful implementation to avoid errors. Dynamic programming is another approach, especially for problems involving repeated subproblems, but it can be tricky when dealing with constraints like visiting all squares exactly once. This method is particularly effective for variations that require the shortest path or have fewer constraints. By understanding these approaches and their trade-offs, you'll be better equipped to handle both the problem at hand and any modifications that might arise. Great job! We've walked through the key aspects of solving Unique Paths 3 and the importance of efficient grid traversal. Keep practicing and applying these techniques to improve your problem-solving skills. Don't forget to like, share, and subscribe for more insights. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!